Welcome to the 32nd lecture of surface engineering. In the previous lecture, we discussed the theory, basically the reason why diffusion coating is, why does it take place at all? Why does diffusional layer form, and what is the mechanism by which diffusion occurs, and what are the elements which are generally applicable for diffusion coating, and so on, and also alluded to some of the practices. But in this lecture, we are going to talk specifics about the diffusion coating processes concerning the three main diffusers here, the aluminum, chromium, and silicon, because as I mentioned in the previous lecture, these are the three most important elements which actually provide high temperature oxidation resistance or protection in aggressive environment to metallic substrates. So, aluminizing, as the name suggests, actually involves material which actually is created or creates a thin aluminum rich or aluminum alloy rich layer. So, this is coated, or the entire purpose is twofold. One is atmospheric corrosion resistance, not necessarily at high temperature, including at room temperature, and also elevated oxidation and environmental resistance against high temperature oxidation and environmental degradation. This process is very much competitive and comparable with the so-called zinc coating on steel. But remember, zinc coating is never exposed to high temperature, whereas whenever you expect the steel or metallic substrates to be exposed to high temperature, like we took the example of the compressor blades made up of titanium, or the turbine blades made up of single crystal nickel alloys exposed to 1050 or so, at such high temperature we require something different than zinc, and aluminum is one of the biggest bet for that kind of a condition. But there is a large similarity because both zinc and aluminum provide a sacrificial layer. So, essentially still the base substrate will remain cathodic, but the top layer of either zinc or aluminum, let us talk about aluminum particularly, will actually react and then form an oxide layer, which so it sacrifices itself to protect the underlying substrate, which is steel or some other alloy. Now, aluminum coating actually is more expensive than zinc coating. But when you are talking about high temperature, you do not have a choice, because zinc is not an effective oxidation protection element at high temperature, because it has a tendency not only for reaction, but also reaching the volatile state. But so for high temperature, this is certainly cost effective. So, the aluminum coating on steel or other metallic alloys can be obtained by hot dip coating, hot dip mechanism, rolled in coating, spray coating, or pack cementation, a solid state process. The important thing is that the coating that we apply actually grows with time. So, when we coat aluminum on steel, then this is how it appears as the cross section. So, essentially you will have a coated layer, and then you have also an interdiffusion layer, where this first layer will be very rich in aluminum, and then aluminum concentration as a function of depth will decrease, and then this is the substrate which is unaffected. So, this layer thickness will depend upon the process parameters, typically the chemical potential, temperature, time, and so on. So, when aluminum diffuses, see, for example, when carbon diffuses in carburizing, it does not form any of the compounds, it does not form cementite for that matter. It diffuses, goes deep inside, and we retain carbon, then we convert that solid solution into martensite by certain heat treatment. So, the hardness and wear resistance comes from the phase transformation product. In case of nitriding, we do form nitrides, and they are the principal reasons for wear resistance, but that is done, the nitrides that form at high temperature, but the application is at room temperature. Now, when you expose steel or nickel or titanium or these elements which have high affinity for oxygen to high temperature, you need elements to form a diffuse coating onto the surface which will sacrifice itself, form an oxide and prevent further ingress of anions, for example oxygen. Now this is done not necessarily through a solid solution layer. So the surface is an alloyed layer which will have higher concentration of aluminum or chromium or silicon onto the surface, but they actually are confined to a thin layer, but they do not necessarily form only a solid solution of aluminum in iron or nickel or titanium. Instead, they are known to form certain intermetallic phases, and these intermetallic phases are very easy to understand as to why do they form when you refer to the corresponding, say, iron aluminum or nickel aluminum or titanium aluminum kind of a binary phase diagram. You will see there are multiple intermetallic phases possible to be formed in these binary systems. So in case of iron, typically one such eta phase that form is an iron aluminide. Now this is beneficial and matter of concern both. Beneficial because they are extremely stable, has very high melting temperature and prevents oxygen ingression or cation, say iron or titanium, to move out. So they form a barrier layer. So this is the kind of barrier layer that we are talking about, and in fact this barrier layer that we form, aluminum rich layer, will grow with time if we increase the residence time in the furnace, in the diffusion coating chamber. So the cross section actually will show us that it is not pure aluminum. It actually is an aluminum rich matrix phase with lot of these intermetallics. The thickness of that layer essentially will depend upon the time at a given isothermal condition, and this K, the constant here, is actually proportional to the diffusion coefficient, and hence one can write this K also very similar to a diffusion coefficient equation and can determine the value of K at a given temperature. So this, once this K is known, then we can predict what would be the thickness. So sigma here is the thickness of the diffusion layer at a given temperature T for at the time of exposure small t. And this is important for us to design the experiment through which we actually use or develop such coating. So there are multiple factors, process parameters, which actually affect the thickness and the integrity of this coating. So as I said, this is an intermetallic layer that we form. So we have to be careful as to what is the time that we expose to, because otherwise the layer that you form will be extremely hard and protective, all right, but also is fairly brittle, and most importantly will have a very different crystal structure and coefficient of thermal expansion than the underlying metallic substrate. So the coating substrate interface will be prone to development of very high stress as the layer of the thickness increases, thickness of the layer increases, and hence there could be spallation or crack formation at this coating substrate interface. So the thickness or the interfacial layer adhesion will depend upon the dipping time and temperature. Now if it's steel, then the carbon content is important, because if you have fair amount of carbon, then they actually not only change the growth rate and morphology, but also the composition of the intermetallic layer that you form. So for low carbon steel, you actually can have a higher thickness of the coating of the and the intermetallic layer. So that means ingression of aluminum faces less difficulty to diffuse in if the carbon content of the steel is low. But if the steel contains a lot of atoms in the interstitial positions like carbon, then diffusion, already the surface is stressed, and further diffusion of aluminum actually will be more difficult. The molten metal viscosity, the bath we are talking about, is very important, and also the wetting conditions, the wettability or the angle of the surface, the angle of wetting also is very, very important. So we may actually at times add certain additives to change the bath composition so that the wettability increases at the surface. The surface roughness, we are talking about the component which is being coated. So roughness of that surface is important because generally the adherence to some extent depends on the surface roughness. In fact, little bit of roughness is actually beneficial because it causes a pegging effect or mechanical interlocking effect. But if it's too rough, then the penetration will be non-uniform and the tip will melt or tip will actually get thicker coating, and as a result the tip may get dislodged because of the brittleness developed. So thickness and morphology will, as I said, can be changed by certain additions like silicon into the melt. So instead of pure aluminum, if you have aluminum silicon, then of course the wettability changes, and actually wettability increases, and bath temperature can be a little lower, but more importantly you actually create a different kind of a morphology onto the surface. So typically if you increase higher and higher amount of silicon, then the depth of the alloyed layer decreases with the distance. So the depth of the layer decreases as we increase silicon concentration in the aluminizing bath. So in industry scale, the process actually is done continuously, not as a batch process, unlike what is done in carburizing or nitriding cases. Not always nitriding, but carburizing, pack carburizing for example, for sure, or even pack cementation processes. Even for aluminum it can be a batch process, but in industry scale when you use a molten bath it can be completely a continuous process. So you feed in sheets of small thicknesses, maybe millimeter less than a millimeter, maybe much less than a millimeter, whatever is the sheet thickness. You don't necessarily bring them in the form of a coil. So you feed in, use a welder to create continuous aluminum sheet, train of aluminum sheet, and instead of coiling you actually make them such loop and you do it through a tower. So you go back and forth and then you accommodate a large length of aluminum sheet in this form. The sheet is fed through these rollers and goes into the furnace. So in between you can have certain annealing process to remove surface stresses or also any other kind of heterogeneity in the microstructure. Then they are subjected to this aluminizing bath, and it goes back and forth into the bath, and this is the residence time here and the temperature are the two most important process parameters. And as soon as the coating is over, you immediately cool rapidly, because you don't want to extend the time of exposure to high temperature or bath temperature or near to the bath temperature, because once the process is over, then you don't want any further diffusion to take place. And to prevent diffusion, the easiest way is to reduce the temperature, because the coefficient will be so low that diffusion effect will be negligible. So you do rapid cooling and then you draw it. There is a online mechanism through which you can measure the gauge thickness of the coating, and then it goes through. So the excess, by the way, the excess aluminum sticking to the surface is removed through an air jet. So the air jet removes the surface excess aluminum and also quenches the surface temperature. So it goes through this kind of a train, and then so we also have a loop tower where certain chemical treatments are done, maybe another protective another treatment to make the coating more adherent, certain types of surface conditioning, the physical conditioning of the surfaces. Then there will be inspection, non-destructive evaluation through radiography or through certain visual inspections and so on. And then the whole coil comes out and then coiled into large, very several kilometer length of coils. So this is the overall process. So typically this is the temperature we are talking about. Temperature can be even higher, but this is good enough depending on the particular application. So we need certain pre-treatment which involves surface cleaning, both acid and alkali bath cleaning, so the surface is fresh metal and not carrying oxide, thin oxide layer due to atmospheric oxidation. Then we do fluxing again to increase the wettability of the surface, so that it's fresh and it actually comes in contact with directly with aluminum, and aluminum can immediately wet the surface and form aluminum and not any mixed oxide or varied composition coating. So then the coating happens in the hot dip bath like here, and so which is a molten bath. So this is a molten bath, and then we have to do the after treatment, which is wiping, air blasting, or removal of excess aluminum, and even rolling to make the uniform coating depth and physical form, and they are withdrawn from the coating bath and then coiled after the mandatory evaluation of the surface condition. So calorizing is a process where, unlike the previous hot dipping, where we apply aluminum from the gaseous or the vapor state, here also we form intermediately compounds of various types, and typically applicable, say, in case of stainless steel. So when you expose stainless steel to aluminum, say austenitic stainless steel, then you actually can form various aluminides or intermetallic phases. So this is comparable to the hot dip aluminizing, but obviously differs in the fact that here the diffusion of aluminum is occurring in the solid state. The substrate is completely, there is no molten layer at all in contact with the surface, and the entire amount of aluminum is coming from the vapor state. So the objectives would be just like the previous case: high temperature oxidation resistance, erosion or abrasion resistance, any protection against carbon ingress. I mean, in various cases, for example, stainless steel or for that matter any other steel or certain materials, when they are exposed to carbon containing atmosphere, there is a possibility carbon can come in, and it may not be beneficial because it may form certain interstitial compounds or change the crystal structure. So carbon ingress must be prevented, and this kind of aluminide layer actually prevents carbon ingression. Also, this is helpful for stress corrosion cracking if to have such aluminide layer, and resistance to corrosion and erosion by any other kind of molten metal. So if you have a bath which actually has this molten zinc or other metals, there could be a large corrosive attack, and that can be prevented by having such aluminide coating or aluminum coating. Also protection against non-metals like these corrosive gases, liquids and ashes and so on. So typically a calorized surface will have very high amount of aluminum. So this is the depth and this is the concentration. So aluminum will be very high. Nickel is generally low, but if you have nickel already in the substrate, that will be fairly high only below a certain layer. So this is the diffusion layer altogether, but within the diffusion layer we see that the surface is enriched with aluminum and having very low content of other elements like nickel, chromium and so on. We are talking about an alloy which contains all these elements. So this is the base level of chromium and aluminum, base level of aluminum. So there is no aluminum in the substrate or very little aluminum in the substrate, but very high aluminum in the surface. So this diffusion layer is because of the principles of diffusion coating. But still, I must point out that this dip is fairly sharp. So the interface, coating substrate interface, is much sharper than, let's say, carburized layer. We can also apply silicon as an element to protect substrate from high temperature oxidation through basically a pack process. You pack the silicon containing elements or substances in a retort, and the intention is to get silicon in the nascent form. So that means you will use certain precursors, say silicon carbide, and also use silicon tetrachloride in the gaseous form. You bubble through the substrate through the mixture containing silicon carbide, and this will liberate silicon, nascent silicon, and that silicon can now diffuse into the surface. So we are talking about in case of aluminum coating, we understood that we are talking typically a few tens to few hundred micrometers of aluminum rich layer, but in the limit it can go to several millimeters, but usually silicon rich layers are less than a millimeter, purely because the silicides that form instead of aluminides are actually slightly more complex in crystal structure and also form slightly more brittle layer. So the silicon layer can be formed on low carbon steels, and I would say anything between 8 to 10%, at the most 12-13% would be the silicon content on the surface. You can get fairly high hardness, but resistance against both corrosion and oxidation at high temperature is the benefit that we derive. Instead of aluminum or silicon, we can use chromium for the similar purpose. Here the precursor will be pure chromium powder with aluminum oxide powder mixed with that, and then we heat this salt into to create this vapor phase. The reactant here will be ammonium iodide, so that chromium reacts with ammonium iodide and forms chromous iodide, which is a fairly unstable compound. Comes in contact with the solid metal, reacts at typically about this temperature, and then liberates chromium from chromium iodide. So iodine comes back into the atmosphere, again reacts with chromium, forms chromous iodide, and so on. So this is how the process continues, and it's a batch process. So beyond a certain period of time, you need to recharge ammonium iodide so that the remaining part of chromium can be utilized. A similar process based on CVD, chemical vapor deposition, can be also used for diffusion coating of chromium on steel or any other metallic systems based on diffusion principles, very similar diffusion principles. Another interesting process, which is not necessarily a diffusion based process, but is used for very similar purposes. So I thought I would just include them here for comparison. And these are called roll bonding processes. In fact, they can be roll bonding, they can be diffusion bonding, and so on. So typically, when you talk of roll bonding, you're talking about two or more metals as parallel layers fed into a roll and then roll together. So when you roll together, if the interfaces between different layers is free from grease or dirt or water or oil, that means completely metal to metal surface is completely guaranteed and without any discontinuity. Then during rolling, the deformation occurs, and during deformation there will also be possibility of mechanically driven interdiffusion. So that means the metal from sheet A diffuses into sheet B, and sheet B atoms can also diffuse into sheet A. So there will be a diffusional layer, interdiffusion layer. So for the mating surfaces should be very well cleaned, ground, degreased to increase the friction coefficient, and any amount of oxide layer or compound layer has to be completely removed by either chemical or physical means. So now you actually do a roll bonding or a cumulative roll bonding when you push them into the roll. In fact, there's no necessity all of them should have same thickness. Actually, the layer to be coated has a much smaller thickness, typically a foil of aluminum, for example, can be rolled together on sheets of metal, even non-metal. So because there's no direct diffusional process, thermally activated diffusional process involved. So we actually rely upon high reduction ratio, and that is when the interdiffusion takes place due to mechanically driven plastic flow. So when somebody sections the diffusion bonded layer, then one sees that there could be a certain amount of diffusional layer. Now, question is why do we need such a process? What's the limitation of aluminizing, chromizing, or siliconizing process? Think of a heat exchanger or large body heat transfer medium. So you're talking about several meters by easily a meter width. To subject such wide and long sheet for diffusional coating, you require a furnace of that nature or a bath of that nature if it's a batch process. If it's a continuous process, then you actually should have so much of consumption, so much of demand to make it batch process. But for smaller substrates, for smaller areas or a limited number of applications, limited consumption, yet wider surface area where we need such protective coating, roll bonding is a typical method. it can be not only necessarily a batch process, it can be also a continuous process. So this is the aluminum metal, and this is a copper metal, and this is how you actually form a clad of aluminum copper through these roll bonding processes. But remember, here the pressure whatever we apply is applied only when you are passing through the roll, so temporary, transient. You can also do a diffusion bonding process where you have alternate layers of, let's say, a gray and a red metal, two different types of metals, and they are pressed together they have uniform thickness and also arranged in some alternate sequence. And now when you apply pressure and then expose to high temperature, so now diffusion takes place all along the surface, throughout the surface at this high temperature for a period of time, and they form complete diffusion bonding. So this is diffusion bonding and not necessarily diffusion coating. This also is roll bonding and not necessarily coating. So you actually retain exact composition of the coating material, and like in the previous cases where the composition varies, various aluminides, various silicides or chromides form. Also, this is, in case of roll bonding, it's a dynamic process. In case of diffusion bonding, it's a static process. So you actually place it inside the furnace, and then it's a batch process where you expose for a certain period of time. So they also have their set of utilities, particularly as I mentioned for large heat exchangers or any other thermal heat exchange processes. So what did we discuss? We discussed about the typical differences between aluminizing and pack cementation. So aluminizing is a hot dip process, whereas pack cementation is a solid state process primarily. So molten bath allows the aluminum, nascent aluminum to come to the surface and then diffuse in, whereas in pack cementation you take it to, take the help of sodium fluoride to take to the aluminum fluoride vapors condition, and then allow ALF to decompose and liberate aluminum to the surface. So obviously in the hot dip process, you are exposing to not only high temperature, but you are guaranteeing a very wide coverage, very good coverage to the entire surface area. The process can be actually faster because it can be a continuous process. So you can pull from one end to other and can make kilometer long strips coated with aluminum and coil them into large coils at a faster rate. We actually must realize that the vapor pressure plays a very important role in this all pack cementation processes or all diffusional coating processes, because the element should have actually very high vapor pressure so that it has a natural tendency when exposed to high temperature to go into the vapor phase and saturate the atmosphere with that particular vapor. So it should have actually a vapor pressure higher than the substrate metal. Aluminum coating is better than galvanizing, not always, but certainly is better than galvanizing at when the temperature is high, at high temperature. The process parameters when we talk of all these diffusional coatings are typically temperature, time, then the concentration of the species or the chemical potential of the species, surface condition, the viscosity of the bath if it's a dip process, and surface roughnesses, physical conditions, and so on. And we have to be very careful about maintaining such conditions or these parameters. So roll bonding is a process where we actually can cover wide area, and we don't necessarily have to expose to high temperature. So room temperature process can cover wider surface area and can actually coat with something whose composition remains the same, does not change. Are the utility or the merit points. The demerit is that it is a rolling process, so you can't do for complex shapes. You can't press under the roll something which has a non-uniform surface contour. So diffusion coating, diffusional processes, diffusional bonding and roll bonding, they are very similar but not exactly the same. In diffusion coating, you are talking without no application of pressure. Both in diffusion bonding and roll bonding, you are talking about application of pressure, but these are essentially high temperature processes and allows diffusion is the primary reason for such coating, and mechanical activation also in diffusion coating, and mechanical activation is the main reason for roll bonding processes. So, these are the processes which we wanted to discuss, so that this is how we actually can create fairly high protection of metallic substrates against high temperature oxidation or other environmental degradation processes. So, thank you very much for your attention.